pH is an indicator of acidity. The body's blood pH is strictly regulated within a narrow range between 7.35 and 7.45. This is because even a minor change in acidity may have devastating effects on protein stability and biochemical processes. Normal cellular metabolism constantly produces and excretes carbon dioxide into the blood. Carbon dioxide combines with water to make carbonic acid, which dissociates into hydrogen ions and bicarbonate. This is an equilibrium, meaning all of the components of the left and right sides coexist at all times, and the concentration of any component is determined by that of others at any given moment. The rule of thumb is, an increase in concentration of any component on one side will shift the equation to the other side, leading to increased concentrations of all components on that side, and vice versa. This equilibrium is central to understand acid-base regulation. Continued carbon dioxide production by all cells of the body drives the equilibrium to the right to generate more hydrogen ions. Because pH is basically a function of hydrogen ion concentration, more hydrogen means higher acidity and lower pH. Normal metabolism therefore constantly makes the blood more acidic. The body must react to keep the blood pH within the normal limits. This is achieved by two mechanisms. Elimination of carbon dioxide through exhalation. The amount of carbon dioxide exhaled by the lungs is regulated in response to changes in acidity. A decrease in pH is sensed by central or arterial chemoreceptors and leads to deeper, faster breathing. More carbon dioxide is exhaled, less hydrogen is made, blood acidity decreases, and blood pH returns to normal. Pulmonary regulation is fast, usually effective within minutes to hours. Excretion of hydrogen ions and reabsorption of bicarbonate through the kidneys. The kidneys control blood pH by adjusting the amount of excreted acids and reabsorbed bicarbonate. Renal regulation is slower. It usually takes days to respond to pH disturbances. Although all of the plasma bicarbonate is filtered in the glomerulus during the first step of urine formation, virtually all of it is reabsorbed back into the blood. Most of this reabsorption happens in the proximal tubule. The amount of reabsorbed bicarbonate in the proximal tubule is regulated via a number of mechanisms in response to changes in blood pH. It increases during acid loads and decreases during alkali loads. While the proximal tubule basically returns filtered bicarbonate back to the blood, the downstream collecting duct generates new bicarbonate by actively secreting acids. As protons are depleted from the distal tubular cells, the equation shifts to the right, producing more bicarbonate, which then exits into the blood. Hydrogen ions secreted into the lumen combine with urinary buffers, mainly filtered phosphate and ammonia, to be excreted in urine. The ammonia buffering system is particularly important because unlike phosphate, which is filtered in fixed amounts from the plasma and can be depleted during high acid loads, ammonia production is regulated in response to changes in acidity, and its concentration may increase several-fold when necessary. Blood pH is the main regulator of acid excretion, but potassium, chloride concentrations, and several hormones also play important roles. Pathologic changes may cause acid-base disturbances. Acidosis refers to a process that causes increased acidity, while alkalosis refers to one that causes increased alkalinity. It's not uncommon for a patient to have several processes going on at once, some of them in opposite directions. The resulting plasma pH may be normal, too acidic, called acidemia, or too basic, called alkalemia. Acidosis may result from inadequate function of the lungs, which causes arterial carbon dioxide to accumulate. This is respiratory acidosis. On the other hand, metabolic acidosis may result from excessive production of metabolic acids, ingestion of acids, decreased ability of the kidneys to excrete acids, or loss of alkali. Metabolic acidosis is characterized by primary decrease in plasma bicarbonate. Alkalosis can also be either respiratory or metabolic. Respiratory alkalosis is caused by increased ventilation, resulting in excessive exhalation of carbon dioxide. Metabolic alkalosis can result from excess loss of acids through the kidneys or gastrointestinal tract, bicarbonate retention, or ingestion of alkali. Metabolic alkalosis is characterized by primary increase in plasma bicarbonate. Thank you for watching. Please feel free to suggest a topic you want us to cover by leaving a comment below.